Okay, so I have shared with you on Classroom a PDF of a worksheet that you're going to need for today's lesson. It looks like this. Hang on a minute. So if you don't happen to have a printer, hopefully you have got a blank page in your exercise book and you can just draw a horizontal and vertical line on it. And there are a handful of these, so you just need to be able to work down your page. So if you are doing it in your book, you just need to spread them out one below the other so that all of the centers are aligned and all of the F's are aligned. And you can see that the only difference between them is that this arrow moves a little bit closer in towards the middle in each diagram. These diagrams are known as lens diagrams, and they are what we are going to use to interpret the data that we took last lesson when we have got a lens that maybe we are unfamiliar with and we haven't used before. And this technique allows us to make a start on what would be a career in optometry if we needed to, where we can actually design lenses to produce images of whatever size we want, of whatever magnification we want, whether they be real or inverted or virtual or the right way up. So this is the goal, to learn how to draw these diagrams today for their predictive power. Okay, so let me go back to the PowerPoint that we were in the middle of last time we were in class. Hang on a sec. It takes ages to share stuff when you've only got one monitor. Okay. Just bear in mind that while I am sharing the PowerPoint, because I've only got the one monitor at the moment, I'm at home today, I can't see the chat. So if you do need to ask me anything, just unmute and interrupt me rather than writing it on the chat. Okay, so what we're looking at here is a lens, and what we are going to do is represent the lens by a pair of lines, one vertical, one horizontally. So technically, the vertical line itself is the lens. You don't have to draw a lens on it to make it into a lens. So the vertical line represents the location of the lens. The horizontal line represents the center of the lens and a ray of light that would pass through it at right angles to the surface at the center of the lens. These are called the principal lines. And then we can note on to this one, which is sometimes called the principal axis. We can note on the principal axis the distance either side of the lens of the focal point. Remember that the focal point is where horizontal rays of light pass through the lens and all end up. You'll see that again in a moment. In some diagrams, the lens is drawn very, very, very small, like they are on the worksheet I've given you. I just want to be very, very clear to you that this isn't the lens. The entire vertical line is the lens. And so if you do draw a diagram and just put a tiny little lens in the middle of it, your rays of light aren't restricted to this bit of the diagram. The vertical line is the lens. This is just a little symbol to remind you maybe what it is. Lots of diagrams don't even put the lens on it. Sometimes they just put an arrow on these vertical lines, and they're supposed to be like the tip of the lens. You can imagine the lens coming out of that bit of line and out of that bit of line, and that's to provide a reminder of what the axis is without putting too much ink on the page, which will mess up the diagram that we're about to draw. Okay, so sometimes it's easier to know what you're aiming for, especially when we're all in different rooms. So just to be crystal clear, I am going to teach you how to draw a diagram that when you are finished will look like this. So your worksheet that you've got in front of you, or your diagram that you've just started to create for yourself, when you've finished it, that's what it's going to look like. It's going to have a second vertical arrow on it to match the one that's already printed on your sheet. It will have two rays of light, this one and this one. And where the rays of light cross, that's where you're going to draw this arrow in. So this is what you're aiming for. This is the goal for all of your diagrams. That's what we're hoping to achieve. So let's just work out step by step by step how we draw the diagram and why the diagram looks the way it looks. So there are some rules for interpreting the rays of light. So here we go. We are looking at rays of light that are coming from the tip of a tall, narrow object. So imagine that you take a stick or something like that, and you go and stab it in the ground, and then you go stand a little way away from it, and you look at the stick, or you put a lens between you and the stick, and the sun's up here or something like that, and the rays of light are coming down and they're bouncing off the top of the stick, and then we are just going to follow two of the rays of light, two of the rays that happen to hit the lens. There will be an infinite number of rays of light coming off the lens, coming off the object at this point. Some will fly up here and miss the lens. Some will fly down here and miss the lens. Some will go over there and miss the lens. Some will go down here and hit the lens, but we're not interested in any of these other rays of light. We're just interested in two of the infinite number of rays of light that are bouncing off this point out of an infinite number of points on the object. So we're just really, really simplifying down the entire picture. Two rays of light only out of all the ones we could consider that are coming from this point on the object out of all the places we could consider. Okay, so rule number one is about this ray of light. This ray of light is a parallel ray of light. It's parallel to the principal axis. It would travel in the same direction as if the object was a very, very long way away. So for objects that are a very long way from the lens, all of the rays of light that hit the lens are effectively parallel. That's not true for a nearby object. For a nearby object, only one ray of light is parallel. All the others travel at angles that hit the lens. This object is close enough that we can notice this angle. This ray of light clearly is not parallel to this ray of light. So for an object far away, all the rays of light are parallel, and we know what happens to them. This object is close by and happens to only have one ray of light that's parallel to the principal axis, but just because it's got one parallel ray as opposed to a very, very large number of parallel rays, the rule is the same. Parallel rays of light, by definition, are bent in such a way that they pass through the focal point. That's the definition of the focal point, that parallel rays of light pass through the focal point. When I'm saying this phrase, parallel rays of light, I mean rays of light that, yes, are parallel to each other, but also are parallel to this principal axis here. So when you draw yours in, I need you to take your ruler now and your pencil and make sure your pencil is very, very sharp, because if you've got a blunt pencil, this isn't going to go well. I need you to place your ruler on your page so that your ruler is lying along this principal axis here. And then I need you to very slowly slide your ruler up your page so that it remains parallel to this principal axis until you reach the tip of the arrow on the very first diagram at the top of the page. And when you get there, I need you to draw in a horizontal line that goes from the tip of the arrow until you hit the lens. Make sure that you draw that line parallel to the principal axis. If you are off by even half a degree, this diagram is not going to work. When you hit the lens, The rule is that any ray of light that hits the lens traveling parallel to the principal axis, like this one, passes through the focal point. So I need you to draw a line to the focal point. And then because there isn't anything at the focal point, there's no bit of paper there, because there isn't anything at the focal point, the ray of light just passes straight through. So your first diagram on your page should now look like that. Incidentally, this PowerPoint will be put on Classroom at the end of this lesson, as will the recording of this lesson. So if at any point I go a bit too fast because I can't see you and I don't know where you're quite up to, or if you get confused, you can watch back the video or you can just work your way through the PowerPoint at your own pace. Okay, that was rule number 1 for one of the rays of light. Rule number 2 is for the other ray of light. Here is rule number 2. Any ray of light that passes through the center of the lens passes through the center of the lens as if the lens was not even there. It's not entirely perfectly true. The rays of light do get refracted a little bit, but what is happening is that even with the refraction, because the lens is symmetrical and because these lines are lines of symmetry on the lens, whatever happens to the ray of light as it enters the lens is undone as it passes out of the same point on the opposite side of the lens. And so whatever refraction or bending takes place as it enters the lens is undone again in exactly the same way as it passes out of the other side of the lens. So it's not true that the lens doesn't do anything to the light. It's just that we don't notice what it did to the light, because whatever it does to the light on the way in, it undoes to the light on the way out. And so here is your second rule. Any ray of light that passes through the direct center of the lens carries on as if the lens is not even there. So I need you to add to your diagram a ray of light that starts at the tip of the arrow and passes through the direct center of the lens and then carries on as if it isn't even there. Now you are going to have to take my word for it, for you are not a trained optometrist, neither am I. You're going to have to take my word for it that every ray of light that starts at the tip of the arrow finishes in the same place. So this ray of light ended up here, and this ray of light ended up here. And now that we've found where two of the rays of light cross, my instruction to you is that all rays of light end up at that point. This is the place where all light that bounces off the tip of the arrow and passes through the lens bends all of the rays of light, all the infinite number that we're not even thinking about. They all end up at this point. And therefore, if you were to place a piece of paper at that point, there would be all of the light from the tip of the arrow would end up at that point, and an image of the tip of the arrow would end up at that point. And we don't really have time to do it today, but you can do it in your own time if you want to. We can play this game for all the other rays of light as well. So if you start a point halfway down the arrow, it would travel horizontally across, it would hit there, it would go through the focal point, and it would carry on over here somewhere. And then you could play it the center ray, and it would go through there, and it would carry on, and it would also end up here somewhere. And you would find that if you played this game for a pair of rays of light that began at the center of the arrow, they'd finish where the laser pointer is now. So the middle of the arrow appears in the middle. And if you did it for the base, well, they're all center rays and they would just go straight through, and the base would end up at the base. And therefore, the base of the arrow is where the laser pointer is now, the middle of the arrow is where the laser pointer is now, and the tip of the arrow is where the laser pointer is now. And what that means is that if we were to place a vertical screen here, we would find that a vertical image would appear at that place. So I need you to finally take your pencil and I need you to draw in an image. And it needs to be vertical. It needs to start on the principal axis and it needs to move downwards to where those rays of light cross. Make sure you're very careful about aligning it perfectly with where the rays of light cross, and make sure you draw a vertical arrow. The object is vertical, therefore all of the points will form a vertical line. If you don't believe me, later on, like I said, play this game for a point in the middle of the arrow or a point at the bottom of the arrow. Right, I now need you to write some descriptive words on that diagram. So for instance, the image is real. The rays of light converged onto a point. They really would land there. They really would make a bright patch of light on a screen if we place the screen there. That is a real image. It really is there. You really could form it on a screen. So you need to write the word real on that diagram. The arrow is inverted. It's upside down. It's pointing downwards instead of upwards. So I need you to write the word inverted on your diagram. And you can see with your eye that it is diminished. It's smaller than it used to be. So you need to write real, inverted, diminished. And then finally, you can actually work out the scale factor. So if you could take out your ruler and measure the height of the image and just write that down in millimeters next to the image arrow. And then if you could measure the height of the object and write that down in millimeters next to the object. This is the object over here. And then on your calculator, you just need to divide the image height by the object height. So you might have something like 12 millimeters divided by 20 millimeters gives you a scale factor of 0.6. And that's called your magnification. If your magnification is bigger than 1, it gets bigger. And if your magnification is smaller than 1, it's getting smaller, it's getting diminished. So your first diagram should look like the slide, and it should have the words written on it. Real, inverted, diminished. Magnification equals, and then whatever your measurements are, 12 divided by 20 equals 0.6, whatever your numbers are. Just going to give you 20 seconds or so to get that finished off. Hi Ethan, I've just checked the chat while you're working. I can't see the chat while I'm showing you the PowerPoint slide. I need to get a second monitor really. So yeah, hopefully you worked out that you're all doing this on the top diagram. Okay, I'm going to assume you're good with that. Okay, I need you to do the same for the next two diagrams as well. So they're all going to look pretty much the same, but the image arrow is going to be in slightly different places and slightly different sizes. But I need you to play the same game. Draw the horizontal ray, the parallel ray, through the focus. Draw the center ray straight through the center. Where they cross, that is the tip of a vertical arrow. Draw it in. And then I need the descriptive words, real and inverted, or real and inverted, and then whether they are diminished, same size, magnified, and measure the heights of the image and the object, and do image divided by object to get the magnification. First three diagrams, please. You've done the first one, now do the other two. When you have finished, could you please just write that you've finished on the chat? So, and when enough people have done that, we'll move on. So just give me a finished on the chat when you're done. I'll put the picture back up so you know what you're aiming for. Okay, we got a handful of people saying that they're done. I'll just wait for a couple more. So maybe take this as your 60-second warning. Okay, let's move on. If you haven't quite finished, you'll be able to finish this after the lesson. Okay, so for the very first diagram, you should have got a very short arrow, and the magnification would have been much smaller than 1. For the next one, I guess this one that we practiced on was kind of similar to the second diagram. And you should have got the arrow for the second diagram was the same size. It was neither larger nor smaller. And for the third diagram, you should have found that it was wrong one, quite a lot bigger. And you can see from the geometry of things why this is. Obviously, this line from the center ray is going to be very, very shallow if it's coming from a place far away. And that's meaning that it's going to cross this first arrow quite near to the principal axis. This object in the second picture is actually twice the focal distance away. And that results by the geometry of it in the triangle here being the same as the triangle here. Those two similar triangles, they got the same angle here, the same base here, and therefore the height of the triangle will be the same. So you can see by the geometry of it that these triangles here are going to be the same size as each other. And that's why the image is the same size when you are at twice the focal distance away. If you get closer, however, you can see that this center ray starts to become steeper and steeper and steeper, which means that it takes longer and longer and longer for this crossing point to arrive. And we get this enlarged arrow. What I've placed on Classroom for you is an applet that you can play with to have a go at how these diagrams would look very, very quickly. So if I just share that with you. So the link to this is on Classroom. You just put your mouse on the little dot on the top of the object and hold down your mouse button, and then you can drag the object around and you can make it taller and shorter, and you can take it a long way away and see that the image is diminished. And then you can bring it closer and closer and closer, and you can see that the image gets taller and taller and taller. You see the focal length here is at 4. So if you place this at 8, you can see that the image is at the same height. And if you bring it closer and closer and closer to the focus, you can see that the rays of light get further and further and further away until finally it disappears off the end of the screen. So you're going to have a much further away image, but it will be much larger as a result. Okay, diagram 4. Notice what happens when I bring this object so close that it actually sits on the focus. So there we go, sitting on the focus. And now let's have a look at the geometry again. This height here is the same as this height here. This is a focal length, and this is a focal length, meaning that this triangle here on the left of the diagram is similar to this triangle here on the right-hand side of the diagram. Well, not just similar, identical, which means this hypotenuse here is parallel to this hypotenuse here. And in fact, this ray of light, the parallel ray that came from the parallel ray here, this ray of light and the center ray of light, these are actually parallel. which means that they will never meet. They will never form a focused point of light on an image, on a screen, and therefore they will never form an image. So on your fourth diagram, I need you to draw in the parallel ray through the focus and the center ray through the center. And I need you to note on your diagram that these two rays of light are parallel and therefore will never form a real image. These parallel rays of light will never form a real image.
So if you're speaking to us right now, you're on mute.
Thank you very much. What I said was, yeah, that applet just crashed my browser, so it kicked me out the meet. Okay, let's have a little look now at the last picture that you need to do. Okay, so in this last picture, we've got the object is now inside the focal length. And so when we draw in the parallel ray, it does what it did before. But now when we draw in the center ray, it's not just that it's parallel now, it's quite clearly diverging. Those two rays of light are absolutely never going to meet. And therefore, this is not going to produce an image. Or is it? Let's have a little think about that for a second. You see, we see parallel rays of light all the time. We spoke a little bit about it ages ago when we were talking about the refraction of light through water. You remember our orangutan friend. So this is a normal thing. Here's some rays of light coming off a fish. And when those rays of light are diverging, we spoke about that when it goes through the water, those rays of light diverge, but our imaging system in our eye, they track the rays of light backwards, and they assume, because our eyes don't know anything about bending of light as it refracts through media, our eyes just assume that rays of light are straight, because most of the time they are. And so our imaging system in our brain traces the diverging rays of light backwards until a point where they think they came from. And that's where our brain will think that an image is. So how does that apply to our diagram? Well, we're going to end up with a virtual image instead of a real image. A virtual image is of an object that appears to be somewhere where it isn't. So let's have a little look at how that works on our diagram. So if we place a screen over here, we're not going to get anything apart from just a general brightness of light. But if we place our eyes here, or a camera, as I showed you last time, these rays of light will enter the imaging system, be it our eyes and brain or the camera, and the imaging system will trace the rays of light backwards to a point that they think the ray of light came from. Now, the ray of light did not really come from here, but our imaging system believes that it did, because that's what imaging systems are. They take diverging rays of light and they trace them back to a point of origin, which means that our eyes, if we place our face down here and have a look, our eyes will believe that there is a tip of an arrow where the laser pointer is. And that'll be true of light coming from the middle of the virtual arrow and the base. And so when we look through the lens with our eyes, rather than trying to focus the image on a piece of paper, when we look through the lens with our eyes, we will see an upright, magnified, but virtual image. So I need you to I need you to complete this diagram. So take a look at how I've done it. You draw it just like you did the first 4 diagrams, but now you draw dashed lines. So place your ruler on the line that you've drawn, and then just extend it backwards as a dashed line. And where your 2 dashed lines meet, draw yourself in a vertical image. And because they're on the same side of the diagram now, you might want to draw it dashed like that, or you might want to write the word image next to it, just so you don't get confused if you're drawing it yourself, rather than if it's, the worksheet. And then some descriptive words, please. So it's virtual now. It cannot be formed on a screen. It needs a separate imaging system to see it, because the rays of light are diverging rather than converging. Which is odd when you think about it, given that we're calling this a converging lens. The other descriptive words then, apart from virtual, upright rather than inverted, and enlarged or magnified rather than diminished. And you can play the same game with your ruler. You can measure the image height and scribble that down on your piece of paper, and measure the object height and scribble that down on your piece of paper. And then you can get out your calculator and you can do image divided by object, and this time it will come out bigger than 1. Okay, so just to summarize again: virtual, upright, enlarged, and the scale factor when you calculate it should be a number that is bigger than 1 now. Okay, this whole thing about seeing through the lens using an imaging system, by the way, works perfectly well for the other images as well. So just to note that we have been noting that if we place a screen here, we will see an object on the screen. But if we don't place a screen here, these rays of light will carry on zooming through the lens past this place where the image would form, and they carry on off into space, and notice that they are diverging away from the tip of this arrow. And if we place our vision system here, so if there's no screen and we just place our eye here, then we will trace these rays of light back to an image that would have been there if we'd have placed the screen there. But if we don't place a screen there, our eyes will still see it as being there. We will still see an inverted object that's bigger or smaller or the same size. So the imaging system will work for these first three diagrams as well. It doesn't just have to be the fourth one. We'll still trace these rays of light backwards to this point. Okay, so last lesson, we met what a converging lens was. If I run this all the way back to the start, we met these converging lenses. We looked at how light behaves through an actual lens. I did an experiment for you in class. And then we have today learnt how to do some lens diagrams so that we can predict what will happen rather than having to do the experiment every time. What I'd like to turn our attention to now for the last 15 minutes of the lesson are the diverging lenses. We're going to do this a little bit more quickly, but you are going to need the second worksheet now. So let me whiz back through this. A lot of slides. Didn't need to, I already had it. Okay, so diverging lenses now. So a diverging lens is thinner in the middle and thicker on the outside. The same thing occurs, that refraction takes place, but now the curve of the surface is the other way. And so rather than bending the light to a point, what's going to happen is that the rays of light are going to be spread away instead. The way that the refraction works means that when the light bends away from the normal, it bends, in this case, upwards rather than downwards. So an example of what that means, we're going to aim to draw some diverging ray diagrams now. So you've got a second worksheet, and the second worksheet looks a lot like the first worksheet, but the lens drawn in the middle is a slightly different shape. Sometimes on some diagrams, they don't draw the lens in the middle. Sometimes what they do is again draw these arrowheads, but all they do now is reverse the arrowheads so that this is supposed to just refer to its opposite to a converging lens. So you can kind of get this idea of curving this way now with those shapes there, kind of curving towards a thinner middle. So sometimes you'll see these upside down arrows. Sometimes you'll see the lens actually drawn in miniature in the middle. But either way we do it, how do we draw the lens diagram? So this is the second worksheet, and we are now aiming for diagrams that look like this. That arrow doesn't look particularly parallel, does it? I should probably edit that. Okay, so the rules are, again, that we are going to deal with two rays of light. Of all of the infinite number that we could imagine, rays of light come down, bounce off in all different directions, but we are just going to follow the ray of light that's parallel to the principal axis and passes through the center of the lens. This is what your diagram is going to look like when you're finished. which looks ever so slightly messy. So let's just be careful about how to draw it. So have the second worksheet in front of you now. There are 4 diagrams drawn on this second worksheet, but the bottom 2 are just the same as the top 2. It's just because when I print them to hand out on paper, I hand out A5 versions. I just cut the A4 paper in half. So you're just focusing on the top 2 diagrams. Okay, here are your rules again. It's the same rule. Parallel rays of light are associated with the focus, but this time, rather than passing through this focus, the rule is that parallel rays of light appear to have come from this focal point. The one that's on the same side as the diagram as the object. So what you need to do is draw yourself in a parallel ray of light. I'm really going to have to move that one, it's upsetting me. Draw yourself in a parallel ray of light, and then when it gets to the lens, you need to put your ruler where the laser pointer is. You need to anchor one bit of the ruler to where the laser pointer is on the focal point on the left, and then you need to line the ruler up with wherever your parallel ray hit the lens, and then you need to draw it diverging away. So that orange ray of light that's on the screen in front of you, it came from where the laser pointer is at that focal point, and it hit the lens where the parallel ray hit the lens. That's what you do with your parallel rays. The rule with center rays is that there's the same rule, they carry straight on as if it's not even there. So you can draw a center ray just like you've been doing for the previous diagrams. And now your diagram should be looking a lot like that. And again, just like we just saw with the bizarrely named converging lens, when you have diverging rays of light, you have to trace them back so that your eye makes a guess for where it thinks they came from. So the center ray actually really did come from where your eye thinks it does. So that one's okay. But the parallel ray doesn't. That one appears to have come from down there somewhere. And you'll see that they cross on the same side of the lens as the object is. And again, where the rays cross, that denotes the tip of the arrow, and you need to draw a little vertical arrow in there. And that means that we end up with a upright, but this time diminished image. So it's much smaller than we thought that it was going to be. So if you look through a diverging lens, you'll see the world. It'll be the right way up and everything will look normal. It'll just look really small. So imagine that there's a tree in your garden. If you held up a diverging lens and tried to look at the tree, you'd see the entire tree through the lens, but it would look like it was just a centimeter tall in front of your face, a tiny little tree rather than the actual big one sitting in your garden. So descriptive words, it's virtual again. Those rays of light are diverging. They're never going to converge on a screen. You're never going to be able to produce a real image on a screen. You're always going to need an imaging system to collect that light and see it. And that image isn't really there. When you make an image on a screen, it really is there, but that image isn't there. It just appears to be there using your imaging system. So it's a virtual image. It's upright. and it's diminished. And just like you've done before, you can get out your ruler and you can measure the height of that image and the height of the object, and you can divide the image by the object to find the scale factor, which again will be less than 0. I've given you two different diagrams, one either side of the focal point. And this is just to emphasize that the behavior for a diverging lens is the same. No matter where you put the object, you will get the same result. And you can feel free to draw your second diagram in, and it should end up looking just like your first. Okay, so like I say, this PowerPoint will be on the Classroom post in a couple of minutes' time, as will the video, so you can watch it back and you can finish off if you need to. I'm just conscious of the fact that we're running out of time a little bit. So I just wanted to show you that I have got a diverging lens here, and you can see it's quite thick at the edges. It's less easy for you to see that the inside is thinner than the outside, but you can see it's not bowing outwards anyway. And then if I just hold it up to the camera, you can see how big I am through the screen without the lens, and you can see you're looking through the lens at me, and you can see that there's a small version of me through the lens. And that doesn't really matter where I put the lens, whether I put it really far away from me as the object, or if I put it really close to me as the object. It doesn't really make a difference. I'm always virtual in that you need the imaging system of the camera to see me. Upright, and the right way up, obviously, but always diminished. That picture of my head is smaller than my real head, no matter where I put this lens. Unlike a converging lens, here's a converging lens. I don't know if you can tell, thinner at the edges, thicker in the middle. And now if I place this quite near to me, you're seeing a magnified version of my eye there. That's where I'm very, very close to the lens. That was the fifth picture that you did. But as I bring that further and further away from me, oh, that's a big magnification of my eye, isn't it? Now all of a sudden it goes upright, and that's because we're now using the imaging system of the camera. I wouldn't be able to produce that on a piece of paper, but the camera is using its imaging system to produce a magnified, upright, virtual version of me. But just note that using the imaging system of the camera, you can always see an image through this, even though it would produce a real image on a piece of paper. We're not bothering to do so. The piece of paper would be kind of here, but we're going straight through that to the imaging system that's the camera. Okay, so you now understand that there are two different types of lenses made up of shaped glass. and you know how to predict the nature of the image that will be produced by placing each type of lens at different distances from the object. And this information allows you to make judgments over what lenses can be used for. So for instance, you might be aware of the fact that these glasses that we view the world through are made of shaped glass, and you might want to ponder on which type of lens do we use? Do we use a converging lens or a diverging lens? And in actual fact, you might know that you have different types of glasses for people who can see things far away, but they can't see things close by. That's long-sighted. And people who can see things close by, but they can't see things far away. That's short-sighted. So do we use the same type of lens for both of those types of glasses, or is one a converging lens and one a diverging lens? We also have magnifying glasses that allow us to see things, small things, in much more detail. Are they converging lenses or diverging lenses? And then the camera on your phone that's taking pictures, it's trying to take the entire world and put it on a tiny little chip, a tiny little photosensitive chip inside your camera. So it's taking a very big world and putting it on a tiny little chip. What kind of lens are we using to do that with? Any of you that do photography will know that lenses can be incredibly complicated things, and that we have to move them for like telescopic lenses and things like that. How does that work? So there's plenty of applications of lenses, and if you're interested in this kind of thing, there's plenty of Googling that you can be doing later on today to find out about it. However, we can follow this up. So over our next couple of lessons, we can answer these questions. What I'm going to do is post to Google Classroom more cover work, I'm afraid, for Tuesday. I need to be in school again on Tuesday to supervise the students who are working in school, like I did a couple of weeks ago. So I'm going to set you some consolidation questions from the textbook for Tuesday's lesson, where you can cut your teeth on this and make sure that you understand all the things that I've spoken about by lenses, but keep thinking about what kind of lenses you would use for different applications and why. And then when I meet with you, our second lesson next week, I will go through the lens in your eye and lens in cameras and lenses in magnifying glasses, and we'll see if you were right and that you predicted the right use of the right lens for the right purpose. For now, however, we're pretty much at the end of this lesson. There's a minute left. So I'm going to close the teaching bit of the lesson now. But what I